For this lecture, we're going to look at how the derivative and the second derivative can give us information about the graph of the original function. We've already talked about that if we have these local extrema, maximums and minimums, that tells us that we have a derivative equal to 0, the maximums and the minimums. So for the first derivative, we've already looked at this a lot. We know that the first derivative equals 0 at the local extrema, or it's undefined. That gives us those critical points. Remember, we looked at the critical points were when the derivative was undefined, or when it was equal to 0, or at the endpoints. And that gave us possible points of local extrema. So that's how we found our local extrema, and we looked at the sign of the first derivative. Remember, we said if it was the function was increasing when it was positive, and the function was, when the derivative was negative, the function was decreasing. So derivative is positive, it's increasing. Derivative is negative, it's decreasing. And we've talked about that a couple of times. So that's just kind of review. So the first derivative can tell us about extrema and whether the function's increasing and decreasing. Now the second derivative can also tell us some important information. The second derivative tells us about concavity. Now, remember, concavity is kind of the slope part, or the curve part of what's happening. For example, this part here, it looks like a mountain. That means it's concave down. It's opened up downward. And this part in here is opened upward. It's concave up. And here we have down and up and down and up. And there's a point along this slope about right here where we switch from being concave down to being concave up, where the where the function changes from, it's got this downward bowl to this upward one. And again here we've got another point here where we switch from being concave up to being concave down again, and here we switch from being concave down to being concave up, and here we switch again, and here we switch again. These are called points of inflection. When we have critical points for the second derivative, where it's undefined, or where it's equal to 0, or at the endpoints if we have a closed interval. Then we have possible points of inflection, and we can test them to see if we have points of inflection, just like we do with the first derivative. Now the second derivative, when it's positive, that means that it's concave up, and when it's negative, that means it's concave down. So we just test either side of these critical points and see if we switch from up to down or down to up, so that we know that we've changed our inflection. We've changed our concavity, so we have a point of inflection there. So the first derivative tells us if the function is increasing or decreasing and tells us about extrema. And the second derivative tells us about points of inflection and concavity, whether it's concave up or down. So let's do an example of this. Let's say we have the function f of x equals, let's do this one, 60x squared plus 18x minus 4. Oh, sorry. Let's try a different one. That's the second derivative. I'm getting ahead of myself in my notes. Sorry. So 5x to the fourth plus 3x cubed minus 2x squared minus 7. All right, so it's a polynomial. It's continuous everywhere. It's differentiable everywhere, so we don't have any problems. It's a smooth curve. So we want to know about this without actually graphing it. So what we're going to do is we're going to look at the first derivative. So the first derivative, we've got 20x cubed plus 9x squared minus 4x. Excuse me. Now we need to know critical points. Well, it's a polynomial, so it's not undefined anywhere, and we don't have any endpoints. We're looking at all the real numbers. So we just need to look at where it equals 0. So we first have to factor. We'll factor out our common term here. So this derivative is going to be equal to 0 when this is equal to 0 or when this is equal to 0. Now this doesn't factor very nicely, so we're going to use our quadratic formula. So here's one of our critical points. And then the other ones, we do opposite b plus or minus the square root b squared minus 4ac all over 2a. So that gives us approximately 0.2756 and negative 0.7256. So these are our three critical points. So what we do is we make ourselves a little chart here. Remember, this is like a number line, and we've done this before. And we test the first derivative. So between 0 and negative 0.7256, we pick a number like negative half, and we plug it in here and see if we get a positive or a negative, and we get a positive. And then we plug in something here like negative 1, so that's going to make us have a negative out here, positive here, so that'll be negative. Between 0 and 0.2756, we've got, say, 0.1. Plug that in, figure out what the sign is, and it's negative. And then for a bigger one, plug in, say, 1, and it's positive. So what does that mean about the function? That means that the function along this interval here is decreasing, and then it has a minimum, and then it's increasing, and then it has a maximum, and then it's decreasing again, and another minimum, and then it's increasing. So this tells us the minimum, maximum, and minimum. Now to know if it's a local minimum or local maximum or an absolute, you have to plug it into the original function and figure out what the points are so that you can compare the two minimums to see see if it's a minimum that's going to be the smallest one. Now the maximum, remember, for a fourth degree polynomial, it's opened either both tails are up or both tails are down in this case, because 5 is positive. Both tails will be up, so there's not going to be an absolute maximum because it's just going to keep increasing. So that would definitely be a local maximum. For the most part, we're just dealing with the local minimums and maximums, not concerned too much about absolute mins and max until we get to the word problems, and those will be a little bit clearer because we'll have more restrictions on our domain. All right, so we've looked at the first derivative. So let's look at what happens with the second derivative. Well, the second derivative, taking the derivative of this is where I got that other one, 60x squared plus 18x minus 4. So our critical points are when it's undefined, the endpoints, and when it equals 0. It's defined everywhere because it's a polynomial. It doesn't have any endpoints because we're not looking at a closed interval, so we just want to know when it equals 0. So we set it equal to 0, and we can factor out a common term here. And then again, we need to use the quadratic formula. So we say opposite b plus or minus the square root of b squared minus 4ac all over 2a. And we get that x is approximately equal to 0.1486 and negative 0.4486. So these are critical points for the second derivative, which means they're possible points of inflection. So what that means is, we give ourselves a little chart here again. We've only got two critical points for the second derivative. So now we need to test. Well, in this middle part, it's pretty easy. The easiest number to pick is 0. Plug that in. We see we're going to have negative. And then down here we can plug in negative 1. And you'll plug that into the second derivative, and you see that it makes it positive. And here we can plug in 1, perhaps, and see that that makes it positive. So what does that mean? The second derivative is positive and then negative and then positive. Well, for the function, what that means is this is concave up. The function is concave up for that section. Then we have a point of inflection. Then the function is concave down. And then we have another point of inflection. And then it's concave up again. Now remember, in this case, all our critical points resulted in points of inflection for the second derivative and mins and maxes for the first derivative. It's not always going to be the case. Sometimes you'll have a critical point where the derivative equals 0, but it isn't actually a minimum or a maximum or a point of inflection. So you have to actually test them all and make sure that you look at that. Now I'm going to draw you a little sketch of the graph. I want you to look at it on your calculator so that you can make sure that you see this, but it's going to be a little bit hard. You're going to have to kind of zoom in. A small window like x from -2 to 2 and y from -8 to -5 will help you see this, because the bottom part is not really clear that this is what happens. So we knew it was going to be both tails up because it's a polynomial, a fourth degree polynomial with a positive leading coefficient. And we knew we had a maximum here at 0 and a minimum at negative 0.7254 or 7256, and then another minimum at 0.2756. Obviously my drawing's not really good to scale. And then our points of inflection, we've got them here at negative 0.4486 and here at 0.1486. So you can see just this tiny little part here that's concave down, and then the rest of it's concave up. Like I said, if you're looking at this on your calculator, make sure you're using a window where your x goes from -2 to 2 and y from -8 to -5, so you can actually see this, because it's not real obvious. But we knew all this because of all this calculus that we've done without having to look at the graph. And we knew that once we graphed it, that's what we're looking for, because we've done all this calculus. So the two need to go hand in hand. You need to be able to look at the graph and do all this stuff so that you can get all the information possible. Your calculator is a great tool, but do not depend on it to show you everything. If you had just looked at this graph without a small window like that, without zooming in and analyzing it, you probably would have said, well, it's just U-shaped, it's concave up the whole way, and there's one minimum, and that's all there is to it. Because it would look just pretty flat on the bottom, unless your window is small enough for you to be able to see that little bitty bit where it's concave down. Because let's face it, concave down, it's only concave down for about half a unit. So make sure that you're paying attention to the calculus and the graph, putting it all together. So first derivative tells us about increasing, decreasing, mins and maxes. And second derivative tells us about concavity and points of inflection. Make sure you've read this section, written down some notes, and maybe even made up a problem for yourself to practice with a polynomial, something simple.